Okay, let me get started. Uh, let me just do one more quick look here. Chat, I thought we set the chat window up. Okay, let's start. I guess first of all, today is the day the homework, the project proposals are due. Are there any questions about project proposals or anything else while we're here? Um, any questions? Okay, maybe I'll talk a little bit more, hopefully, at the end of class, just about the next step in the grading and stuff like that. But I think I'll wait for a slightly bigger crowd. Any questions about anything at all before we get started? Okay, last class we finished up on visualization, and we started talking about models. Um, and again, in principle, we've talked a lot about cleaning data and visualizing data and stuff like that. What are some of the issues when it comes to building models? That's what I'd like to talk about for the next class or so. Um, and one thing that I find interesting is to think about different philosophies of modeling, different ways that you should think about building models. And when people talk about bias variance trade-offs and Occam's Razor and things like that, they're really talking about model philosophies. And so I'd like to talk about how many people here have heard of Occam's Razor before? Okay, any one person on TV waving. Okay, Occam. Who was Occam? Occam was some guy in the like 11th century, some monk or something like that, and he was trying to come up with a philosophy of why things happen, and you know, as I remember foggily, one of the question would be, God does this or God does that. Sometimes they were phenomena that didn't, necessarily need, calling God in order to explain. And so Occam's philosophy was that the simplest model is best, simplest explanation is best. And that is kind of, when we think about modeling, that is an argument that when you build a model, you don't necessarily want to use all the variables that you have. There's two different philosophies. One possibility is your goal is I want to produce the model that will get me the highest score on Kaggle. And if you do that, then maybe you use all the variables, you do certain things. But if on the other hand, you believe that the simplest explanation is best, you probably want models where there is some incentive to minimize the number of parameters. A lot of the times people are building models based on data that they have. Just because they have the data doesn't mean it's relevant to the problem that they need to do. So, one thing to keep in mind is that when we look at machine learning methods, they will differ wildly upon whether or not they're trying to build simple models or trying to build, models with large numbers of parameters. Deep learning models have millions or billions of parameters. Okay, Occam might not be so happy with those kind of models. Um, but there are other machine learning methods that we'll talk about, where things like where when we use linear regression, there are techniques called, which we'll talk about probably in a week or two, that employ penalties to reduce using features that are not very relevant, things like lasso regression and ridge regression. And, in general, it's not a bad idea to think in terms of, methods that are going to reduce the number of features it actually uses. It probably also is a good idea to make sure that when you look at what features you're using, thinking to yourself whether or not it the feature should make a difference, I think is a perfectly reasonable thing to do. One argument is you let the model figure it out, whether, like what were you guys trying to, if you're trying to predict sales, you could imagine some, on the sales data, was there any feature that struck you as completely irrelevant when you were trying to predict for a store? The what? The store what? The store ID, okay? So one question would be, like, you could imagine that the store ID was a feature, okay? That's a number. Now, should the store ID be a feature in your model predicting it? Okay? Quite likely it may be an arbitrary number, right? It could be a number that reflects, what you call it. It may be reflecting, if the numbers were given sequentially, it might reflect the age of the store. Or if the stores were sorted by number of sales, maybe it would reflect bigness of score. In any case, you would like to think that the store ID probably shouldn't be in some principle in a model like this, okay? Often if it is in there and it makes a big difference, that's probably cheating on some level, and that's kind of what I mean by a sniff test. Any questions about Occam's Razor? Okay. Occam's Razor, by the way, in life is also an argument against conspiracy theorists. Okay, so there's certain people who will believe that, that there's a small number of people who are controlling things, and they involve, there's some massive complicated conspiracy that is why the economy is the way that it is. It could be that, or there is a simpler explanation. According to Occam, you would make that the choice of which was right by which was simpler. What's another philosophy of modeling that comes up? And it's a recognition that there is a bias variance trade-off when you're modeling something. What is bias? Okay, I think people know that bias is kind of a bad word and should be a bad word. But what is really bias? Bias is this idea that you're making an assumption, okay? You're making errors based on an assumption of, your model. If you are assuming that one group of people are not as good as another, that is showing bias. That is an assumption, and that is, kind of limits your worldview. Variance is kind of an error that results from being too sensitive to, let's say observations. Bias comes from the idea that at the beginning you know how the world works, and damn it, I'm going to build my model like that. Variance means I know nothing, and I am going to just listen to my data completely. The first problem, if you have, let's say, a bias problem, you tend to produce models that underfit the data, okay? If you assume that there is a linear relationship between the input variables and the output, that's what you're doing in linear regression. There you have a danger of underfitting the world if the relationship is not linear, okay? If you say, I know nothing about how the world works, but I've got 5 training examples, and I'm going to use those to be my guide to the world. You're likely to have a model that's going to fixate on the wrong things in the training data, okay? And that's what we mean by overfitting. So when you have a model, you should be aware of, what the possible sources of bias are. Bias here, I'm referring to mostly, let's say, the restrictions in the shape of the model. Bias can also come in because if your data is drawn from one distribution that isn't right, that's a similar model. You're assuming that a similar problem. You're assuming the data that you have is representative of the whole world. When I think about models, they're kind of, data-driven models are obviously more likely to be overfit, okay? So if you have a model that's purely based on analyzing data, you have a bigger chance of having your problems there. If you have a model that works according to some kind of theory that you developed, okay, which is a perfectly rational thing. If you think about economics, there's theories of how the world works. There's theories of how unemployment and inflation are related to each other, okay? You could use one of those theory models. You could try to predict what the relationship is given that it exists from theory. That's kind of based on a first principle understanding of the world. Models where you think you know why things are happening, the problem may be bias. Problems on data-driven models may be more due to variance, okay? Any questions? There's this quote that I always like about modeling, okay, which says that all models are wrong, but some models are useful, okay? And that's true of theoretical models, first principle models. It's true of any kind of a prediction thing, okay? Our goal is to try to produce models that help us make useful predictions, not perfect predictions, but useful things. Any questions? Okay, fair enough. The other philosophy of modeling that I want to talk about comes from this guy Nate Silver's book. I know I waved it around the first day of class. Nate Silver is this guy who who analyzes who got his start. He runs a website called 538, and he got his start analyzing election polls. Actually, he did some things before that, but he got famous for analyzing election polls. When there is an election, you have dozens of different pollsters polling, 50 different states, okay? And they're asking slightly different questions to slightly different people. And on some, candidate A is going to be doing better than candidate B, and on some, candidate B is doing better than candidate A. His job was to try to produce a prediction of who was going to be president. And this shows him in his, back in the election of 2012, his website would feature a graph here that would show you every day. It would make a prediction of how many electoral votes did every candidate get. Okay, and at this point, Obama was leading Romney, and he came up with a probability of who was going to win. Now, this is a prediction of what the expected number of electoral votes were, but he always couched it with a probability of what was the chances of winning. He would, in his forecast, he would do simulations, and this kind of showed that what was the probability of ending up with a certain number of electoral votes. Okay, so he's good at modeling, and he has some some philosophies in his book that I think are interesting to talk about. One is that when his job was to try to predict who was going to be president, his model did not produce a yes or a no. His model would produce a probability distribution. What was the likelihood that each candidate was going to get a certain number of electoral votes? Usually, when you're trying to make a prediction of something, if you try to say what's the likely thing to happen, A or B, just saying A or B is probably less useful and less accurate than some kind of a probability of what the right label is. When his argument that I think is true is that when you think of any kind of a classification problem, you should be thinking of it in terms of a probability distribution of what can happen rather than a single prediction. Um, and, how confident you are about a particular prediction is important information. There's some situations where the forecast of what something is going to be, you're very, very sure of. Sometimes you're not so sure. And, if a problem is hard enough, the accuracy of the model does not necessarily have to be that good. If you could predict whether the stock market was going to go up or down tomorrow, if you got it right 55% of the time, meaning you got it wrong 45% of the time, that would be enough to be a rich man. Okay? So recognize that a good model still might not do very, very well in some absolute sense. But if you know how much to trust your predictions, how much uncertainty there is, it becomes a lot more valuable. So again, he would be telling us that if we were going to build models, models should return probabilities. Okay, and again, we talked about what probabilities are. They're between 0 and 1. They sum to 1 over all things. The important thing is that a probability, a confidence level, is basically a way of telling you how certain you are about the outcome of something, not just what is most likely. And some of the techniques you guys have done for modeling may not immediately lend itself to, or you may not think about probabilities, but the probabilities are probably there if you look at it. You can imagine, let's say you're trying to build a classifier. Is it going to be A or B? The classifier returns A or B, but it also returns typically some kind of measurement of how far the value is, let's say the criteria is from the decision boundary. So let's actually have in this class or in anything we've done, have we done any classification of things where you had to predict A or B? Maybe not yet. I guess most of the things you guys were doing in here were regression assignments. You were trying to predict values rather than predicting labels. Or am I wrong here? Malware was a good example. Malware was, were you guilty of being infected or not being infected? That's a classification thing. Now, the answer, infected or not infected, probably is less useful than a probability of being infected. Okay? And, in the course of doing that, your classifier, if you did something like logistic regression, gave you a measure of how far, in some sense, you were from the decision boundary. Not only am I on the infected side of the boundary, but by how far. And we talked about the logit function before, and we'll talk about it again when we talk about logistic regression in more detail. That was a way of turning, if you had a criteria function that measured how much do we believe that it's in class A, the logit function was a way of turning that into a probability, and that might be a criteria that is useful to score these things on. Any questions or comments? So thinking in terms of probabilities is a good idea. One other thing that Nate Silver does that I think was very important for coming to trust the models that he built to try to predict the elections is that his models were live, okay? They were always running, and they were always updating the predictions based on when new information came in. So again, he's trying to monitor the election, who's going to win, okay? if the model is good, there should be a couple of properties that you would have. One is, as you got closer and closer to the decision being made, you should be getting more and more confident. Okay? If you know who's going to win the election, is Biden going to win re-election in 2020 and in 2024? Well, no one should have a very good answer to that. They don't know if he's going to be running. They don't know if any of the candidates involved are still going to be alive then. Okay? You would expect a prediction like that should have increasing confidence as you got closer. And if you saw your prediction over time, that would be one way of telling it. One question, if you look about your model, if your model is live, is it always retraining itself as you get new data? Models for things, especially data-driven models, get out of date with time. And if you have something where you train a classifier and you fix it, and then the world goes on, likely there's going to be a problem as the world changes. And as a user face, can you see what your past predictions are? Because I think that one of the good things about trying to predict something in the future and keeping it live is you get to see how this changes over time. This was a picture I took from Nate Silver's website in 2016. 2016 is when Trump was running against Hillary Clinton. And at this point a couple weeks before the election, he had Hillary Clinton as with likely a probability of winning of 86%. Okay? And as time went on, actually, if I remember what played out in the election, it got tighter. And ultimately, I think that at the end of his predictions, it was something like 69 to 31%. Okay, was what it was before the election. Now, what I can tell you was when I was showed this slide to students when I was teaching this in 2016, one of the students sent me a mail of someone who was very upset because because they were analyzing the election data, and to them it was so obvious that Clinton was going to win that they were accusing Nate Silver of basically not of trying to lie to keep the election looking close, so people would keep going to his website. Obviously, who won the election? Was it Clinton or Trump? Trump won the election. Okay, so was this a good or bad forecast by Nate Silver, given the fact that Trump ended up winning? I frankly thought he did a great job that election. Okay, first of all, he had Trump as having a higher probability of winning than just about any other forecaster. If you have a 31% chance of winning, what is the chance that you're going to win in terms of coin flips? That says that line of like 1 out of every 3 times you're going to win, right? If you have a biased coin you lose 70% of the time, you win 30% of the time. How amazing is it that you win? The answer is not that amazing. Okay, it's a quite reasonable event. Okay, and if you just think of it as a label, he got it wrong. As a probability thing, I think he got it kind of right. And when you look at this graph, this person who was complaining that Hillary should have had a 100% chance of winning. If you look at this graph, to me, it's obvious that person was wrong. What does this graph show? This graph shows that the prediction of who is going to win the presidency was clearly very volatile. Okay, it was a race that was changing, the outcome was a close race, and it was one changing quite rapidly. And when I look at this situation and saw how much it had moved, when I was, when I was sitting here, where did this go? Given when you saw the ups and downs of the race so far, how confident should you be in the current prediction here? Okay? It's clear that it had moved by, large amounts in relatively short periods of time, and that this was by no means in the bag at that point. Any questions about these predictions? Okay, I think this is a good example of how showing the past predictions helps inform how you should interpret the future. I think it was a good example of how having a probability of winning, okay, instead of just a label, was a lot more informative about what was going on. Any questions? Other thing that Nate Silver does when he tries to predict the elections, which I think are very good, is that when he makes a prediction, he's also looking at not only the polls, but he's looking at other models of how the election should go. Okay? So, for example, there are prediction markets. What is a prediction market? This is a website where you can go to bet on who is likely to win the election. Now, the odds that you get on who is going to win the election change over time. If a lot of people are betting on Trump, the odds start to swing in Trump's favor. A lot of people bet on Clinton, the odds would swing towards her. Do the prediction markets do a good job of predicting who's going to be president? Well, some people say yes, some people say no, but it's a different source of information. It's a different model than just the polls. And by looking for other models, having multiple models, and seeing if they kind of agree on the picture, gives you a better idea of what's going on. So many of you, for example, I know when you're trying to train a model, you might say, oh, I've got all this data, I'm going to build one out of linear regression, and I'm going to build one out of support vector machines and decision trees and things like that. And it could be you take the best. Another idea is maybe you take all the models, okay, and you see whether they're giving you the same kind of a prediction. Okay, there's different techniques. There's something called boosting, which is a machine learning technique that takes a bunch of different models and combines them, and maybe to make a better model from the aggregate of these. Okay, and if you have a world where you sensibly have multiple models, you should look at what all of them have to say, if it's an important enough decision. Any questions? One thing in particular, which we'll talk about soon, are baseline models. And even the baseline models are very, very simple models. If the very, very simple models are saying something different than your complicated model, maybe it's something that you give a second look to. Here is a famous example of a modeling problem that happened. Something having to do with Google flu trends. Okay, Google, we all know, is a smart company, and Google has infinite data about everything in the world that matters. One thing that, again, we now live in a world where I'm wearing this mask because of COVID, but the usual epidemic that you have in the United States every winter is a flu, the influenza, and it kills, a large number of people each year. And, it's a public health thing. It's kind of important to be able to predict, is there going to be a big flu outbreak this year? If flu is on the rise, you better work harder to get people vaccinated. You better make sure that medicines are available. So the Center for Disease Control spends a lot of money and effort to chart how many flu cases there are in the United States and where they are. And that's kind of governed by the red line. Now the trouble is Google, the data in some sense for CDC comes from doctors asking how many flu patients did you see? The trouble is that's a little bit slow. It would be nice people get sick before they go to the doctor. Wouldn't it be great if we had a way of predicting how many people were going to get the flu earlier, maybe even before they get it, okay? So Google had this idea that said, if people have the flu, what happens? They start to feel bad. What do they do when they feel bad? They type in they type into their search engine, I have a headache, give me what should I do? Okay, I have fever, I'm coughing, I have chills, what do I do? So Google had the idea where, what if we kept track of a bunch of terms that are associated with illness and and then counted what was the relative frequency of this. Any part of the country where there were relatively more queries concerning illness today than there were yesterday, if it was a statistically significant difference, that probably means that there's more sickness in this place. Maybe there's an outbreak here. Okay? And so Google built a model that was, trying to predict flu outbreaks. And once they sort of got it right, from like here, see how well the Google model tracks the number of flu outbreaks that you get. Okay? Until it was great for about a year and a half or so. Then it started to diverge a little bit. And then it went crazy. And Google was predicting the end of the world, predicting there was going to be a really terrible outbreak when there was nothing special going on. Why did this happen? Okay, when they did a post-mortem of the model, one thing that happened was that Google, in an attempt to get more engagement, okay, started making search suggestions. Okay, you typed in headache. Okay, maybe you're interested in knowing about coughing. Maybe you're interested in knowing about fever. And people started clicking these buttons more. And what ended up happening was the suggested keywords that came up were being clicked more. That caused it to look like more people were entering these search terms. And then it kind of went crazy. Okay? So what went wrong with the Google model? Well, for one thing, they didn't recalibrate it. They didn't retrain it as the world changed. A lot of times when you have models, the world changes under you. And unless you are retraining the model, you won't see that. Okay? Any questions about that? Okay. Now, again, when I think about making models for things, there's two kinds of models. I mean, there's many kinds of models. But as a first approximation, I'd say that there are two kinds of models that are interesting to me. There are things that I call first principle models that are based on theory, based on my knowledge, that show kind of bias about the world. And there are data-driven models, ones that are only based on correlations and machine learning and things like that. I think that it's good to have multiple ways of thinking about a problem. If you have an idea of how it works, it's often good to build a theoretical model, okay? And then compare it to your data model or, use your theory. You should be aware of what you're trying to do. Certain modeling methodologies, like simulations, depend upon how the world works. Okay? Certain other ones like machine learning depend only upon what your data is. Okay? Both can be effective, but again, you should know what you're doing and know whether there's another way to think about it. Any questions? Okay. The last thing on this particular set of lecture notes that I want to talk about today has to do with baseline models. Okay? You guys are going to do projects. For many of the projects, maybe not all, probably not all, but many of them, you're in some sense building a predictive model. Okay? And there becomes a question of how should you know whether your predictive model is doing something interesting? One way to tell we talked about was statistical significance tests. If you're doing better than chance, then something's going on. But often people build complicated machine learning models that don't really do better than very, very simple kind of heuristics or rules. Baseline models are models that are kind of, I will say, the simplest reasonable model that you can build to make some kind of a prediction. And maybe the first thing that I encourage people to do when you're building a modeling problem is to start by building a baseline model, maybe building a couple of baselines that you will be able to compare yourself to in the future, okay, to see whether they are better. So suppose you're trying to build, let's just say, with the malware thing, you were telling me we were building a kind of a classification model where you had to try to build a label as to whether the guy had malware or not. If you were building a model, what would be a reasonable baseline based on relatively little knowledge to try to predict whether somebody had a malware? Linear regression on a lot of data starts to be smart. Okay, okay. So at some point a linear regression model is smart. What would be a simple dumb model to do it? Okay. What if you say everybody has malware? If there's more people have malware than don't have malware, declaring everybody as having malware is a perfectly reasonable baseline. Okay, the majority class, the bigger of the two classes, is a perfectly reasonable baseline model. Is there any other model that might be reasonable to think about if you were going to try to make a prediction of malware or not? Well, maybe you flip a coin, okay? And at every point you flip a coin and say this guy has malware, this guy doesn't. Are these good models? Hopefully not. Hopefully, if they're not paying you a lot of money for these kind of models. But unless your model is does better at this, okay, then what you have is of limited value, okay. And so it's important to learn how to build baselines. What if you had a regression model? Did any of you have to? Were there any assignments in here where we had to make a prediction of a numerical quantity as opposed to a label? What was one? What? Predict sales. Okay. What would be a baseline model to try to predict sales? Okay. A relatively simple, relatively dumb model to predict sales for a company, for a store. One is maybe a measure you're saying maybe if you had a one variable model, you're telling me that a store with more customers is going to sell more. That may be what you're telling me, right? that sounds like a good first principle model, right? I know that store sales, I think, come from people going into the store. If I knew how many people went into the store, I would be able to predict sales. That might be a baseline. Are there any other simpler baselines that you might give for the store? Yeah? What is the average sales for a store in the whole fleet? That would be the dumbest one, right? What were the average sales in this store since the beginning of time, right? That would be a perfectly good baseline, okay? What was the sales last week? That would be a good baseline, right? And now that one probably is a hard one to beat, actually, unless you really, if there really are effects of weather or whatever else that you're coming in here. So thinking about baseline models and building up a suite of baseline models is a good idea, okay? And again, if you have multiple labels, pick them uniformly or at random. Pick the most common one. Pick a simple single variable model. That was like customers in the store going to sales. Pick the previous point, okay? Basically, thinking in terms of baseline models before you're doing anything complicated with machine learning and all that, I find is a very, very good thing. Okay, on TV I see the coin flip model. Yes, I like coin flips. Okay, as basic baselines. Any questions? Okay, any questions about any of this modeling philosophy stuff we've talked about so far? Okay, what I would like to now talk about, I'd like to go to I think I'm going to stop that lecture. The other stuff was, let's say, we're a little behind now, so I'd like to try to catch up a bit. Let me come back here. Sorry about that. No. And I wanted to now get into model validation. Okay. You guys were, whenever you build a model, okay, you're going to need a way to score how good your model is. And, I guess on the last homework where you were trying to pick sales, we said something about like, we were interested in, I think it was the root mean squared error of the log of sales. That was, I think, the main model that error criteria that you guys were trying to think about. But I think, learning to evaluate models and evaluating models in a fair way is an important thing. So I'd like to, for the rest of the class, kind of go through some of the statistics that tend to be meaningful in evaluating both what I'll call classification models, the ones that produce labels, yes or no, nowhere or not, or regression models that produce a numerical prediction. Different statistics are appropriate for each one of these kinds of things. So first, let's look at what happens when you're evaluating the malware, non-malware, a classification problem. And when you look at metrics for evaluating classifiers, there tend to be kind of four things that can happen on any given example. Typically, every element in your training or evaluation set has a real class to it. It either was malware, or the machine either has malware or it doesn't have malware. And that's, its actual class. When you make a prediction, your prediction can either be right or wrong. And that defines four possibilities. When something is in the positive class, positive is usually the class that we say is smaller, or if they're the same size, maybe it's the one that we care more about, or we pick the thing randomly, arbitrarily. Okay, but we'll say that one of the classes is a positive class, one of the classes is a negative class. This is if we have a binary classifier. Okay, we'll talk about multi-class classification a little later. If you predict, if the thing really is a positive and you get it right, that's a true positive. If the thing is really negative, not positive, and you say that it's not positive, that's a true negative. These two cases correspond to your classifier being correct. The cases that are more subtle, or not more subtle, but that require a little bit more care talking about, are what happens if we get it wrong. There are two kinds of wrong, of things being wrong that can happen. We will say a false positive is when there is a negative item, okay, a thing that's actually negative gets labeled as predicted as positive. So a false positive is when a negative item gets labeled as positive. A false negative is when a positive item gets labeled as, when a positive item is labeled as negative. Okay? Any questions about that? I always find these notations confusing. Okay, so I reserve the right to get this wrong during class, and you guys have to keep me honest. Okay? When we are evaluating a classifier, is a false positive as bad a mistake as a false negative? Is a false positive as bad as a false negative? Is a false positive worse than a false negative? Okay, or is it better? What? The answer is it depends, okay? That there are different kinds of problems where calling something positive, incorrectly might have a different result than calling something negative incorrectly. What happens when somebody, let's say you have a cancer classifier, you're going to take a look at my biopsy, and they're going to try to tell me if I have cancer, okay? Now, what would a false positive be? What would a false positive be in this case? It is someone who did not have cancer who is being told that they are sick, right? What is a false negative? A false negative is someone who does have cancer and is told that they're healthy. Is that right? Which is a bigger mistake? Okay, in this case, you're telling me a false negative is a bigger mistake because there's this guy who you might have saved who's now going to die or something. Okay, what is the consequence of the false positive? That would be someone who is that is someone who is healthy, who is now going to get a terrible fright. They're probably going to do all kinds of horrible operations on them. But again, I think I still agree that in that case, the false negative is different than the false positive. But that's not always the case. Can anyone think of a case where we are a false positive is not such a big deal? Okay. Well, anyway, look, you could, okay, first of all, you could imagine, let's think about it. You could imagine, let's say, like a potential customer, okay? If it's a relatively low stake decision, okay, maybe making the right classification, it doesn't matter so much whether you you have a false positive or a false negative. It should be clear that that this, depending upon what the stakes are, it can make a difference which mistake is which. And that's why we're going to, have to come up with different evaluation metrics to charge whether things are false positives or false negatives. So I find it useful to think about classifiers as in terms of threshold classifiers. What is a threshold classifier? Typically, your model is going to come up with, for every example, some kind of a chance of positiveness. Maybe it's a probability of being positive. Maybe it's computed some feature or score that correlates with positiveness. Okay? We can think about, in this case, your classifier is going to, generate for every example a score. You can think of them as being defining then the true positives and the positives and the negatives as defining two different distributions of scores. If the scores of the positives and the scores of the negatives were the same, the distributions look like this, you're not going to have a very effective classifier. If the distributions look like, this, then everything's great. There's a perfect separator between them. Okay? More likely, you get a world where there is going to be some overlap between the distributions. In a threshold classifier, what is it going to be doing? It's going to take a score. It's going to take the score and then cut a line. Okay? Are you above or below the line? Below the line, we're going to call it negative. Above the line, we're going to call it positive. We do this kind of a threshold situation. Which is the best place to draw the line? It depends upon, again, what the cost of false positives are and false negatives are. If we drew the line at this place, what are the true positives, true negatives, and so forth? The true positives are the blue examples on that side. The true negatives are the red examples on the other side. The false positives are the negative examples that, fell on the wrong side of the classifier. The false negatives are the the positives that fell on the wrong side of the classifier. Okay? Now, so any questions about what this threshold classifier is? What is the right threshold for a given, in this case? What is the best threshold to set for your particular problem? Okay? Yeah? Well, we don't like false positives and we don't like false negatives. The right one depends upon how much don't we like false positives and false negatives. Okay? Does everybody agree in the cancer case? You were telling me you didn't like false negatives. Okay? So the right place to draw the cutoff depends upon if, let's say, positives here were the ones that got cancer, if you didn't like false positive, if you didn't like negatives, okay, maybe you would draw your cutoff over here. If you had some kind of a classifier that was going to identify if someone was a terrorist, but it was kind of noisy, and they were going to take this and shoot the terrorist. What would you like to do? You probably would like to draw the cutoff something like over here. So you got a non-trivial number of terrorists, but didn't shoot too many people by mistake. Okay? Exactly which the best threshold is depends upon what you're trying to do. And that's why we're going to need to have different statistics for it. Any questions? So what are statistics? The the accuracy is the most obvious statistic of a classifier, which is basically going to be the right predictions over the total number of predictions you make. So true positives plus true negatives over all four possibilities. This is the accuracy of a classifier. Okay? Now, when I think about any one of these metrics, we're going to go through a couple of these different metrics. One of the things that when I think about these things, I like to think about them in terms of whenever I have a classifier, I ask myself, what would a monkey do? A monkey is one that's basically just going to is a classifier that's going to guess randomly. Suppose, let's say that I have it's going to toss a coin and what you call it, get the basically half the time say it's positive, half the time say it's negative. Okay. What would the accuracy be when you toss the coin randomly? One thing to note is that when you work these things out, you got to be careful about whether or not there is a skew in the distribution. Okay? Notice that there's going to be a difference of a world where half the items are positive and half the items are negative. That's a different world than where 95% of the positive items are positive and 0.05 are negative. What happens, though, to accuracy when there's a different skew of positive and negative things? Okay? If I toss the coin heads on, what you call it, 50-50, okay? The claim is that the accuracy is always going to be 50%. How many true positives are there going to be? Okay? If we toss the coin, if we toss the coin, okay? Let's think of it. If we just flip a coin 50-50, what do we have as a relationship between true positives, true negatives, false positives, and false negatives? Are they all equal? No. Okay? That's not going to be true. Because why? Okay? Suppose, let's say that almost everything, let's say that these were the negatives and these were the positives. Suppose there were very, very few positives. How many true, if only a small fraction of your examples were positive, what fraction, how many true positives are there going to be? What?
95%.
Well, in this case, the true positives are the ones that were positive and got classified as positive. My claim, the number of true positives is going to be the number of positives divided by 2. If you flip a coin and ask and say, heads or, say positive or negative with equal probability, right? How many true negatives are there going to be? I'm going to claim it's going to be the number of negatives, actual negatives there were, divided by 2. If every time it was a negative, I flipped the coin and said heads or tails, I would get half of that right. What about the other cases, though? How many false negatives are there? Let's say false positives. What were false positives? False positives were things that we labeled as positive that were negative. Okay, how many of them are there going to be? Well, anything that was negative, okay, that we didn't call negative is a false positive, right? So this is going to be n over 2, and this is going to be p over 2, if I have it right. If you work that out, the accuracy is going to come out to be a half, regardless of what the split is between p and n. Okay? If you flip your coin randomly. Any questions? Is there a way you could do better in predicting the accuracy, in getting a higher accuracy on a classification? If you knew that the results were skewed, if you knew that most of the people in the world are healthy and don't have cancer, if you want to make a high accuracy classifier for cancer, what should you do? Label everybody as healthy. Does everybody kind of see that? If I labeled everybody as healthy, okay, how many true positives would I have had? 0. How many true negatives would I have had? Every single negative. I would be doing, in this case, 0.95. Okay? So if you know which class is bigger, picking the bigger class is going to get me an accuracy above 50%. Okay? Any questions? Does that mean that a classifier to predict whether somebody has cancer should say everybody is healthy? Well, the answer hopefully is not. Okay, and so what do you need to do? You need to have another statistic. What is the precision? Okay, the precision is the number of true positives divided by the number of what do you call it? The number of true positives plus false positives. What is a false positive? A false positive is someone who was negative, who you called positive. Is that correct? Okay. So this is someone who was healthy, but you called positive. Okay. If you said everybody had cancer, okay, then you would get all positives, and all the people who really had cancer would be here. But all the people who didn't have cancer would come in would come in here, and this would lower it if cancer was rare. So the precision is going to say, when I make a call that you are from the positive class, how often am I right? Okay? And that monkey that got scored 50% on accuracy, okay, if only 5% of the people had cancer, the monkey would achieve a precision of of 5%, which is the same thing that you would get if you always said everybody had cancer. Any questions? So if being right when you say it's positive is important, precision is a better statistic. Any questions? Recall, okay, is if we think about the cancer case, in the recall, why we were willing to do what? We wanted to tell some people, we were willing to tell some people that they had cancer, even if they didn't, in order to make sure that we caught the ones that really had cancer. Okay? So if we want to make sure that we catch the kind of that we're right on positive measures, okay, we use a statistic like recall, which is the number of true positives divided by true positives plus false negative. A false negative is somebody that really had the disease, right? A false negative is someone who was positive. In recall, we want it to be the case that we catch the people that the ones that do have the disease, we catch them and we call it to them. Okay? And we're willing to tolerate a certain fraction of false negatives. Okay? Recall is the number of true positives over all the people called positives. Okay? And again, in the cancer case, it's an important thing. Now, if you said everybody had cancer, what would we have? The true positives, every positive would be up on the top. How many false negatives were there? 0. So we would get perfect recall. Okay? Recall is saying how much, what fraction of the people did we actually, of the people that were positive, did we identify as positive? It's clear we want to have a high recall, but we also want to have a high precision. And these things kind of work against each other. Okay, it's easy to have a high recall if you're willing to have a low precision. Okay, it's harder to have a high precision. Okay, if the cases are small, if one class is small. Okay, but there is a combined statistic. If you need to only use one statistic on your classification problem, the one that is probably most popular is something called F-score. F-score is a combination of precision and recall. Precision is how often am I right on the hard case? Okay. Recall was of the people with the hard cases, how often did I get it right? Okay. Both of these are important. The F-score is the harmonic mean of the precision and the recall. Okay. The F-score is we're used to taking the idea of arithmetic mean. We could take the average of precision and recall. But the harmonic mean has the property that it is always lower than the arithmetic mean. And so a consequence of that is it's hard to get a high F-score unless you do well on both of these. That's really what's kind of required. Okay, so F-score is kind of the single probably most revealing statistic when you've got a classifier like that, because it kind of does capture notions of accuracy while also capturing the skew. Any questions? Okay. So what is the story? Basically, F-score tends to do the best job, but all four work together to get a good classifier. And accuracy can be a good statistic. It's usually the simplest statistic and the one that's easiest to defend, but it only makes sense if the class sizes are the same. When you've got one class size that is small, it ends up getting, the accuracy is very misleading. Any questions? Okay. There is another kind of statistic that is very useful in analyzing the performance of threshold classifiers, which many of your classifiers ultimately are. You're computing some kind of a measure of goodness, of positiveness. And one way to read a situation like this is to now, again, right now, to get this thing right, I'm going to have a line that's going to start over here and move to the right, okay, because I happen to have the positiveness with bigger scores. What am I saying? Let's say we live in a world like this. In a world like this, we have a classifier, okay, an objective function that generated this histogram. It separated the positive elements from the negative elements. Okay? What is the ROC curve? It is going to be a graph of the true positive rate over the false positive rate. Okay? So it's kind of a measure of cumulative true positives versus cumulative negative false positives. Now, suppose I drew my line here and I said everything on this side was positive and anything on this side was negative. What would be the situation? Okay? My true positive rate, well, I never made any mistakes. Does everybody agree? My false positive rate, well, basically, at this point, okay, let me just get focused here again. Let's maybe draw it over here. Let's draw something that's a classifier like this. What is good if I drew, let me erase that. What if I had my classifier like this? And he said on this side it was positive, excuse me. What would I like to say? At this point, I have classified a bunch of examples as positive. Most of the examples that I've classified are positive, and most of them are right. What I'm going to want to say is, up this way, I'm going to give myself credit for every example that I classify correctly that is positive. And I'm going to give myself a tick in the other direction for every example which is a false positive. If you look down here a little bit carefully, you'll see there's a little red there. There's a little red there. The red ones to the right of this line are false positives. What should be clear is if I sweep my line, my threshold line to the left, as I go with this, I'm going to get more and more elements labeled positive, and my true positive rate is going to go up. I'm going to eventually start crossing over negative examples, and when I cross over a negative example, my false positive rate is going to go up. Does everybody see that? What happens if I move my line all the way to the right? Okay? And all the way to the left. Everything is going to be declared positive, including all the negative examples. So over at this point, what is my classifier? If I say everything on this side is positive and everything on that side is negative, I've got all my true positives are labeled there, and all my false positives are labeled there. So I'd end up getting a point here where, of all the positive examples, they're all positives. And of all the negative examples, they are false positives. What I want to convey is the idea that maybe I'm saying this, slowly or, too cleverly. It should be clear that as I slide over my classifier from right to left, I'm going to get from a point where, if I have my classifier here, and I say this is positive, nobody got classified, there's no true positives, but there's no true negatives. If my classifier is to the right, all positives are true positives, and all negatives are true negatives. As I slide through this thing, my false positive and false negative rates are going to trace out a curve. Okay? And each point on this curve represents a possible threshold for a threshold classifier. And at every given point, okay, there is a positive rate and a negative rate that is realized by that thing. Okay? I could pick my classifier anywhere along this curve, and if I do, that is a possible threshold I can pick. Which is the best of these thresholds to pick? It depends upon how much I value false positives versus false negatives. But the possible settings are each reflected by a point on this curve. Any questions about what I mean by the ROC curve? Okay. If you understand what I said, okay, what should be clear is that in any ROC curve that is, a sensible one, is going to start at 0, 0. It is going to end at 1, 1. And it is going to basically be a monotonic function. It's only going to go up and to the right. And if you do that, the better curve is going to be one that has the most area under it. Okay? In an area where, what would be the best possible ROC curve? The best possible ROC curve would happen if we had positives and negatives and they were disjoint distributions, right? Then as I slid over this thing, it would be positive, 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 positive. I got all the positives. I now keep sliding. Oops, I'm falsely calling a negative. I'm calling a negative positive, negative positive. In the best possible ROC curve, I would have a curve where the area under this thing was 1. 1 times 1 is 1. In the worst possible such curve, okay, I mean, if I did something perverted, okay, and I instead swept my line the wrong way, I guess I could get a curve with 0 area. But if it was kind of, I was making random choices, if my curve here if my objective function was a random thing, then basically every time I swept over, I'd be equally likely to cross a positive or a negative. Okay? I would end up with an area under the curve of a half. So the area under this curve is a measure of how good your threshold classifier is, your objective function is. Okay? If you have an area under the curve of 1, well, then there's a threshold where you're never going to make a mistake. If your area under the curve is high, you've got a range of possible thresholds, all of which are doing a good job picking up positive examples, okay, before they start to turn negative. Okay? If you've got an area under the curve of 1/2, then you're in some trouble. Okay? Then you've got basically random behavior. Okay? Any question about that? So the area under the curve is a good measure of how good a classifier is. Any questions about the AOC measure? Okay. Okay. Any questions now quickly about project things? Okay. I noticed that we have the projects are due today. You hopefully will get tomorrow, if everything goes according to plan, you will get some kind of message from us by email telling you which projects you were supposed to peer review with some level of instructions. You will be given 3 projects. You will be given a form. Okay? Your job is to write out helpful criticism to help the people who are doing those things do better projects. That's kind of the main goal. What did you find convincing? Were there things that they didn't that maybe what did they find in what did you find interesting in what they're proposing to do? Were there weaknesses like they didn't have access to data that you can have some ideas about? The goal here is to try to provide constructive criticism and compare the three proposals that you get. Okay. My goal here, the main objective is which will make a better which looks like it will make a better project. Okay. So people who look like they're doing interesting things, they should do better. If it looks like they say they're going to do interesting things, but you don't really believe them because they don't look like they have data, they don't look like they really know what they're doing, that's a thing to comment on. But recognize that these students are your peers, they are other students, they are friends of yours, even if you're anonymous. So be nice and don't say, say constructive things, say genuine criticism, but don't make it personal and be reasonable. Any questions about that? How much weightage of points is given to the peer review? Okay, so what is going to happen with the peer review grades? What typically happens, what happens is I see what the results are. Okay, each proposal will be read by a, TA-like person or perhaps me, and it will be read by the students. Each proposal should be reviewed by multiple students. Okay, generally speaking, I give half the weight to the instructor review and half the weight to the peer review. Okay, but I also look for consistencies. If I see that that some project is rated quite differently on the peer review rather than the instructor review, I flag that and I take a look at it. Okay. Sometimes I learn that the TA could not be trusted on that project. Sometimes I learn the students really didn't seem to have an idea of what was fair. Okay. But that's basically what I'm going to be doing. In general, my hope is that it's going to be half and half. I have found this is the most accurate way in the past, but I look for anomalies. I will also tell you that the degree of correlation between the proposal grade and the final project grade is less between the instructor, is less on the proposal than on the final project. Why is that? Well, that's because the proposal is still kind of vacuous. You haven't done that much work at this point. You don't know. The final product is a lot easier to grade. Okay? This is one reason why the proposal doesn't get that much weight, as much weight as the progress report, which does not get as much weight as the final report. Okay? Because I do recognize that the proposals are somewhat harder to evaluate because in some sense you're trying to predict the future on them. But try to provide as solid a feedback as you can, and don't be afraid to learn by looking at other people's project proposals. Maybe you have ideas there that will help you with your own. Okay? So if everything goes right, you'll hopefully get these tomorrow. I'm going to want you to turn them around by Sunday, okay, so that we can get feedback to you by next class. That's kind of what I really want, okay? Because I know many of you can't work on your projects, obviously, till you get feedback. I know you also got other things in your life. But I do want to get the feedback back to you as quickly as possible. So go ahead, and that's going to be the plan. Any questions? Yes. Each group should submit one proposal. Okay? And if you submitted multiple ones, I believe that there's ways that we're going to screen this out. Okay? But I think you're supposed to have submitted only one per group. Okay? That's why the form presumably had the team members on the form, right? When you submitted it. Is that correct? That's how we're going to analyze that. Okay? Any questions about that? Any other questions about the project from here? Okay, if not, thanks for your attention, and we will talk next class. And again, in my dreams, hopefully there will be feedback on projects then. Okay, take care. Thank you very much.